Okay, hi everyone. This is a continuation as promised. So the two examples we did in class today that involved, this appearance of the variable x. Like this is what's new for us today, right? This variable x is new, is making a new appearance. The two examples we did the two series behaved divergent or convergently, and X played no influential role, right? And my big dramatic buildup at the beginning was talking about the fact that when you have this X as a variable, not only does the series defy classification, right? It defies potentially behavior depending on the value of X. So what we're going to do here is set up the ratio test for absolute convergence again, and I want you to replay me when you've gotten to the point where your argument of the limit is simplified with all the superfluous absolute values addressed, okay? And then replay me. Okay, here I am, right? When I've addressed the fact that -1 to the k need not even appear in my absolute value of the a sub k plus first, or the kth term, because it will always be, as Thomas said, +1. That's superfluous. When I address the fact that, k plus 2 and k plus 1 will always be positive, the only portion that requires the absolute value is right here, right? It's the absolute value of x minus 4. Okay, let's now deal with the limit. So nothing new from what we did in class. As k approaches positive infinity, again, what does this approach? This approaches 1, right? Degree 2 polynomial over degree 2 polynomial, lead coefficient is both 1. So at the end of the day, as k approaches positive infinity, this is new for us, everyone. What does this limit approach? The limit approaches the absolute value of x minus 4. This is new. Up until now, the two examples we did in class, you'll notice that the entire argument of the limit approached either 0 or positive infinity because of where because of where k fell in this simplified k plus first over the kth term. This is not what happened here. In this case, as k approaches positive infinity, the entire argument, right, approaches 1. Oh, I guess I'll write the 1 down. 1 times the absolute value of x minus 4, or just the absolute value of x minus 4. This is where you're going to want to tend to very carefully. Now, we're going to say this. If the limit of the ratio of the absolute value of terms approaches x, the absolute value of x minus 4, what do we know about the ratio test for absolute convergence for the series to converge? We know that we want this limit to be less than 1 for convergence. Okay? We want the limit of the k plus first over the kth term, and that limit in this case is the absolute value of x minus 4. We want that limit to be less than 1 for convergence. Well, what does it mean for the absolute value of x minus 4 to be less than 1? Look at us, absolute value inequality. I believe we're in the world of math too. That means we want x minus 4 to be between 1 and -1. If we solve for x, that means we want x to be between 5 and 3. What we've just said here, everyone, is if x is between 3 and 5, the series will converge. And this kind of ties to what I said at the beginning of class about the role of x. When we have series where the variable x now makes its debut, it is possible that not only does the series defy classification, its behavior, convergent or divergent, could very well change depending on x. If x is between 3 and 5, the series will converge, okay? By extension, if x is, say, for example, bigger than 5, right? Let's say x equals 17. What that means here is if x is 17, or if x is, say, -40, the series will diverge. So we now have these values between which x has to exist for the series to converge. But here's my question for you. What if x equals either endpoint of this interval? Okay? What if x equals either endpoint of this interval? So these values here, I am taking, this is the endpoints of this interval. That's where I got this from. All right, let's take a look at that. Well, let's see. If x were to equal 3, if x equals 3, let's take a look. I'm going to put x equals to 3 because after all, if x equals 3, we want to know what happens to this series if x equals 3. I'm going to put x equals to 3 into x. -1 to the k, I have to scroll back and forth, and then I have 3 minus 4 to the k, and then I have all over k plus 1 squared. Okay, let's clean this. Just like before, so much of our work with series has to do with just tending to the minutia, not losing ourself. In this case, the world of pre-algebra, -1 to the k times -1 to the k all over k plus 1 squared. I'm going to ask one of you or all of you or any of you, could this numerator be simplified some more? This looks ridiculous, right? Let's see. What is -1 to the k times -1 to the k? What does that equal, Thomas? You were very good with the -1 to the powers today. Yes, -1 to the k times -1 to the k. It always equals what number? +1. We now have this situation. All right, so the question is, if x equals 3, what happens? Well, let's see. If x equals 3, we get this series. And now we're in the world that existed before x made its debut. This is an old school question, right? We know what this will do. We know this will behave like who? Who will this behave like? It will behave like the infinite series 1 over k squared. And we know this converges by p-test. Because p is bigger than 1, right? Which converges by p-test. Okay, what about if x equals 5? Let's take a look. If x equals 5, let's plug it all in. My new series becomes, let's see, the summation from k equals 1 to positive infinity. I have -1 to the k times 1 to the k all over k plus 1 all but squared. Okay, let's clean it up. Clean it up. Thomas, what does this equal up top? Thomas was on the ball with the -1 to the k today. Positive infinity. What does it equal up top, everyone? Yes, it's just -1 to the k, because 1 to the k right here always equals 1, right? All over k plus 1 squared. And now we're back in our old world. We're back in the world where a series doesn't have an x. And we ask ourselves, okay, what kind of series is this? This is what kind of series, everyone? It's an alternating series. For alternating series, we have only one test we can use. It's the alternating series test. By inspection, do you see that the terms, the absolute value of the terms are decreasing and approaching 0? This converges by AST. So let's just back up and zoom out here. What we said initially, when we applied the ratio test for absolute convergence, we got ourselves here. We said, well, for values of x between 3 and 5, the series will converge. But what happened is, when we tested the endpoints of the interval, we found, well, actually, there are more values for which this series converges than the values between 3 and 5, non-inclusive. It turns out that, in this case, at the end of the day, the series converges for, look at this, values of x between 3 and 5, where both endpoints are inclusive. Okay? This, when you find the final interval of convergence, what you have found here is called the interval of convergence. Okay, now there's a couple of questions I know that are burning. I know Melissa would probably have this question. I also know Juliana would, and Tyler would, and probably more of you too. I only think about them today because they asked questions similarly. Question number 1, Ms. Yam, when you use the ratio test for absolute convergence, and when you get to this point here, do you always have to check each endpoint? The answer to that question is yes. There is the answer. The other question is this, Ms. Yam, when you check the endpoints, is it possible for, say, one endpoint to yield convergence and the other to yield divergence? The answer to that question is absolutely yes. So, for example, it is absolutely possible that those inequalities could have looked like this, right? Is it also possible that when you check the endpoints, both of them yield divergence? Absolutely yes. And in that case, your interval of convergence would look like this, right? Bottom line, do we always have to check the endpoints of the interval at this juncture? Do we always have to do this? 100% absolutely yes. Okay? When you are asked to find the interval of convergence, you absolutely must check the endpoints. If you are asked, I'll tell you this is so lovely. If you are asked to find something called the radius of convergence, okay, this is good news for you. If you are asked to find the radius of convergence, I'll write it out first. Finding the radius of convergence does not require you to test the endpoints. Okay, and here's why. The radius of convergence is merely the distance from, is merely the okay, one more time. The radius of convergence is merely half the distance of the potential interval of convergence. So here, do you see how the interval of convergence is going to be 3 to 5, possibly inclusive, possibly exclusive, possibly one and the same? The entire interval of convergence is 3 to 5, which has a length of 2. The radius of convergence, in this case, it is just equal to half of the potential IOC, which is the interval of convergence, irrespective of inclusion or not inclusion. So here, at this point, you would say the radius of convergence equals 1, right? Because the entire distance is 3 to 5, which is 2, cut it in half is 1. Boys and girls, even if the endpoints yielded divergence, the radius of convergence would still be equal to 1. So that's nice, because if you're asked a radius of convergence question, guess what? You don't have to check the endpoints. But guess what? For tonight's homework, you absolutely do have to find the interval of convergence, okay? As promised, thorough screencast, lots of vocab, lots of ideas, more importantly, really, really important ideas, okay? I don't mean important like more important than, I don't know, like the next genocide. I mean, that's far more important and critical, but I mean important in our luxuriously worry-free world of math, important ideas. Homework will be up on the teacher page.